Consider an electron in one-dimensional infinite potential well of width 1 nanometer. Calculate the separation between the two lowest energy levels and the wavelength of the photon corresponding to a transition between the two energy levels. Given h is equal to 6.6 into 10 raised to minus 34 joule second, velocity of light c is equal to 3 into 10 raised to 8 meter per second, mass of the electron m is equal to 9.1 into 10 raised to minus 31 kilogram. So for an electron, we have studied an equation for an electron in one-dimensional infinite potential well. Then the expression for the energy of the electron in the nth state is given as En is equal to n square h square by 8mL square, where n is the energy level, h is the Planck's constant, m is the mass of the electron, and L is the width of the potential well, infinite potential well. And this equation can also be represented as h cut is equal to h by 2 pi, or it can also be written as En is equal to n square h cut square pi square by 2m L square. Instead of h, this becomes h cut square 4 pi square. Then it will be En is equal to En square h cut square pi square by 2mL square. In the problem, it is given that the width is 1 nanometer. That is, L is equal to 1 nanometer is equal to 1 into 10 raised to minus 9 meter. And calculate the separation between the two lowest energy levels. Two lowest energy levels, we are taking it as n is equal to 1 and n is equal to 2. For the n is equal to 1 level, the equation is E1 is equal to 1 square h square by 8mL square. And for n is equal to 2, it is E2 is equal to 2 square h square by 8mL square. Then the separation between the two lowest energy levels, that is the E2 minus E1. E2 minus E1 is, E2 is 2 square h square by 8mL square, that is 4 h square by 8mL square, minus E1 is 1 square h square by 8mL square, that is h square by 8mL square. And this equation, it will give 3h square divided by 8mL square, and substituting the values, 3 into 6.6 into 10 raised to minus 34 the whole square divided by 8 into 9.1 into 10 raised to minus 31 into L is 1 into 10 raised to minus 9 meter. It is 1 into 10 raised to minus 9 the whole square. And this gives the energy in in joule. And this is approximately 1.81 into 10 raised to minus 19 joule energy. And when it is expressed in electron volt, 1 electron volt is equal to 1.6 into 10 raised to minus 19 joule. Therefore, this joule is 1 joule is 1 by 1.6 into 10 raised to minus 19 eV, and therefore 1.81 into 10 raised to minus 19 joule is 1.13 electron volt. And the question, the wavelength of the photon corresponding to a transition between two energy levels. Corresponding to this energy level, the wavelength of photons emitted. That is, we have the equation h nu is equal to E2 minus E1, and therefore h nu can be written as hc nu frequency c by lambda is equal to E2 minus E1. It is given as 1.81 into 10 raised to minus 19 joule. That is 1.81 into 10 raised to minus 19 joule, or therefore lambda is equal to, that is hc divided by 1.81 into 10 raised to minus 19, that is h is 6.6 into 10 raised to minus 34 into c is 3 into 10 raised to 8 divided by 1.81 into minus 19. And this will give approximately 10.99 into 10 raised to minus 7 meter. This is the equation. And the next problem is The work function of barium and tungsten are 2.5 eV and 4.2 eV respectively. Check whether the materials are useful in a photocell and which is to be used to detect visible light. So in the case of photoelectric effect, we have the equation, photoelectric equation, H nu is equal to H nu 0 plus half m v square. So here H nu is photoelectric effect, means emission of electron from the surface of certain materials when light of suitable frequency is incident on it. Here H nu is the energy of the incident photon, and H nu 0 means is the energy required to release an electron from the metal, and half m square is the kinetic energy of the electrons, emitted electrons. So this is according to the conservation of energy, and in this equation this H nu 0, it is called the work function, and this H nu 0 can be defined as the work function is the minimum amount of energy required to release an electron from a metal, and this work function, it depends on the nature of the emitter. So the work function of barium and tungsten are 2.5 eV and 4.52 eV. Check whether these materials are useful in photocell which is to be used to detect visible light. The visible ranges we know that 400 nanometer to 700 nanometer, or 400 into 10⁻⁹ meter to 700 into 10⁻⁹ meter. This is visible range. In this equation, W is this work function, we have to know whether the energy comes in this range. So we are first calculating the energy corresponding to this 400 into 10⁻⁹ meter, and then the energy corresponding to 700 into 10⁻⁹ meter, and after that we are checking whether this energy in electron volt comes in this range. And first the energy corresponding to 400 nanometer visible light, that is the energy is equal to Hc by lambda, or H is 6.634 into 10⁻⁻34 into C 3 into 10⁸. Lambda is given this one, 400 into 10⁻⁹. This is the energy in joule. We are considering it in eV because the energy given is in electron volt. So for converting it into electron volt, we are dividing this with 1.6 into 10⁻⁹. This is the energy in electron volt. This is the energy in electron volt, and it will give us approximately 3.106 electron volt. 106 electron volt. That is the energy corresponding to 400 nanometer wavelength is 3.106 electron volt. Then the next energy we are considering the energy corresponding to 700 nanometer wavelength, 700 nanometer visible light. It is E is equal to Hc by lambda, that is 6.634 into 10⁻⁻34. H C is 3 into 10⁸ divided by lambda is 700 nanometer, 700 into 10⁻⁹ into corresponding energy in electron volt 10⁻⁹. This is the energy in electron volt, and this gives a value 1.77 eV. So the energy is 3.106 and 1.77 eV. This is the energy range, and in the question only the barium comes in this range, 2.5 eV in between 3.106 eV and 1.77 eV. So only the barium is suitable for used in photocell to be used to detect the visible light, and for the tungsten it is 4.2 eV. 4.2 eV electron volt means it is beyond this limit, beyond this energy limit. and beyond this the visible light range. Hence only barium is suitable for using in photocells. And the next problem is show that the phase velocity of a relativistic electron is Vp is equal to C into 1 plus m0 square c square lambda square by h square the whole raised to 1 by 2, where lambda is the de Broglie wavelength. We have the equation for a relativistic electron. For a relativistic particle, the energy momentum relation can be represented as E is equal to root of p square c square plus m0 square c raised to 4. m0 c square is the resting mass energy of the electron, p is the momentum, is the energy. And this equation, we are familiar in the relativity, we have the equation mc square, but m is equal to m0 by root of 1 minus v square by c square. We are just modifying this equation and cross multiplying this term and modifying and substituting the values of E is equal to mc square and momentum is mv. Finally we get the equation, the energy momentum relation in relativity. So from this equation the energy is equal to root of p square c square plus m0 square c raised to 4. But the phase velocity is given as phase velocity, it is represented as Vp. Phase velocity means it is the velocity of an individual wave in a wave packet, or it is also called wave velocity, and it is represented as omega by k. And but we know that the omega is the angular velocity. It can be represented as 2 pi times frequency, and k is the wave vector or the propagation constant. It can be represented as 2 pi by lambda. Then we know that the nu E is equal to h nu, or nu can be represented as E by h. Therefore in this equation instead of nu it is 2 pi E by h divided by 2 pi by lambda. Okay, but we know that 2 pi cancels and E by h into lambda. But we know that the de Broglie's equation lambda is equal to h by p, or we can write it as, therefore this lambda by h by lambda is equal to p. H by lambda is equal to p, and then we can write it as h by lambda as p, that is E by p. That is the group phase velocity or the wave velocity is E by p. And here we are considering the values of E by p. A is given p square c square plus m0 c raised to 4. That is the phase velocity Vp is equal to root of p square c square plus m0 square c raised to 4 by p. Or we are taking c square outside and taking this p into the square root. There's c into p square by p square plus m0 square c square by p square the whole raised to 1 by 2. This will give. Then c into this will, that is taking the c square outside of the square root and multiplying keeping this p inside this square root. Then we get c into p square, this one, and it will can be written as m0 square c square by p square. Then here the whole raised to 1 by 2. Here we are multiplying this equation with a c square and this with a c square. Then it will give m0 square c raised to 4 by p square c square the whole raised to 1 by 2, c into 1 plus m0 square c raised to 4 by p square c square the whole raised to 1 by 2. But we know that here the de Broglie wavelength is expressed in de Broglie wavelength lambda. De Broglie wavelength lambda. So in this equation we are replacing this p with the de Broglie wavelength. We know that the P is equal to h by lambda. From de Broglie wavelength, substituting the values of P here. That is, Vp is equal to C into 1 plus n0 square c raised to 4 divided by this P square is h square lambda square divided by c square the whole raised to 1 by 2, or this will give C into 1 plus this c square and cancels, the remaining term will be n0 square c square lambda square by h square the whole raised to 1 by 2. This is given in the equation. That is, the phase velocity is equal to c into 1 plus n0 square c square lambda square by h square.